you would like to use the Leibniz theorem using square root, then it is extremely difficult. So, for example, here look at this, y into root over of 1 minus x into equal to root over of 1 plus. If you start to use Leibniz theorem here, in the left hand side product of two functions and right hand side is a nth derivative of root over of 1 plus x. It will be difficult to establish this relation. So, what it is done, first we usually try to avoid the square root or any fractional part. So here look at this, after taking square we are getting y square 1 plus 1 minus x equal to 1 plus x. Now if you differentiate this, you will get this one. And here in the first part, y equal to this, here look at this, this y square, you know that y square equal to uh, 1 plus x by 1 minus x. Now if you multiply this y square equal to 1 minus 1 plus x by 1 minus x. So still there is one y is multiplied here. After substituting we are getting this. Then again if you multiply y by both sides, again you will get y square here, and here y by 1 minus 2x, no problem. And y square again 1 plus x by 1 minus x, substitute it, then you will get this. Next part is very simple. Just use the Leibniz theorem and several problems are solved. That for this type of example, you have to this one, prove this one. So what you have to do? You have to take the n minus 1th derivative, because here started with yn. Here already done one derivative. So you have to use Leibniz theorem for n minus 1th derivative. It is not probably solved. You have to do. Yes. Yes. No. So you have to do it. Is very simple. That's why I have not solved it. But first part is very important. If you any type of problem, whenever even if it is, if the in your question, if just in your question, even if it is not given that, so that this first and hence so that, then also I would suggest you that first establish this type of relation and then use the Leibniz theorem. If in the given question there is no square root, then if suppose it is y equal to 1 plus x by 1 minus x, then you don't have to do anything like that. Then just apply, this is 1 minus x into y equal to 1 plus x, then apply Leibniz theorem. But usually when we find that there is any root, square root, etc., then do this one. This first avoid to eliminate the square root, then use this one. Okay, next another example. First, look at the problem. What you have to do, if you get any idea, then I will explain. If x equal to sin 80, y equal to cos 80, then show that this. Any idea how you will proceed? This
First
function is give.
dx by dt, dy by dt, then dy by
Yes,
dx.
yes. Then dy dx. Suppose here it is x dot, that is dx dt. Then y dot dy dt. Then dy dx. And if you have any t function of t, try to eliminate that one, and then you will get a relation like this. Not this relation, you will get a relation like this, y1 into something or y2 into something. Then apply the Leibniz theorem. So first, what you have to do, you have to differentiate with respect to t with respect to y, then find dy dx. If then eliminate all the function of t in terms of x and y, you have to express in terms of x and y. Then use Leibniz theorem. If you get a relation like this, just I'm giving, I don't know what will be the relation. Say for example, x square minus 1 y1 equal to 2y, suppose. Then you have to take n plus 1 times derivative using Leibniz theorem for n plus 1 time, because here it is n plus 2. Remember this one, not nth derivative, or many times I have seen that written just for the nth order derivative use leave this theorem, but no, you see actually n plus 1 time derivative of the function. This is another this is one example. So some problems are solved on successive differentiation based on, mainly based on Leibniz theorem. Okay, next come to the next problem. Try to understand this. What is the problem? Also solve it, but first try to understand by yourself. Then only you will check whether it's possible or not. Then you can proceed through this process that method that I have discussed here. What is the function? Tan inverse x, and your you have to expand it as in powers of x minus 1. So here, if you look at this if you consider fx equal to tan inverse x, so consider general function fx in powers of x minus x. So what will be the expansion? This is the Taylor's theorem for x, for the function fx in powers of x minus x, that is about the point a. In powers of x minus a means what? Expansion of function using Taylor's theorem about the point A, about the point A. That is, suppose if A is a point here, any point x is here, so expansion of the function fx about this point. Okay, then what? So here in powers of x minus 1, so here A is actually what? A is actually 1, and fx equal to what? Tan inverse x. So here look at this, fx equal to tan inverse x. So fa, that is f1 tan inverse 1 pi by 4. Next x minus 1 f dash means fx equal to tan inverse x, f dash x equal to 1 by 1 plus x square. So f dash 1 equal to 1 by 2 half. Similarly for this one, x minus 1 by whole square by 2 factorial f double dash a. F double dash x means first you have to differentiate 2 times this one. Hence f double dash a equal to 1. Probably this is minus half. Minus half. Similarly, if you would like one more, you can find the f triple x, that is third order derivative of the function, and then substitute here, you will get the expansion of uh, fx equal to tan inverse x in powers of x minus 1, in powers of x minus 1. If it is inverse of say for x minus 2, then what you have to do? A equal to 2. If it is, for example, about the point half, that is inverse of x minus half, then A equal to half. But the method is same. Okay, next problem check. What is the next problem? Just a moment. Just check it. Can Okay, so next one is the uh, estimate the value of root 10 correct to 4 decimal places using Taylor's theorem. Root 10, you know that if it is 9, then a square root of 9 equal to 3. But when it is 10, 11, etc., then you will get approximate value. You will not getting the exact value. So, for example, here you have taken, it is taken, sorry, here it is taken square root of 10, and here fx equal to, then we have to take by Taylor's theorem. So fx equal to square root of x, and if you consider fx plus h, you know that the expansion of the function fx is this one, and x equal to what? Sorry, fx equal to root x. So fx plus h is what? X plus h whole to the power half, and that expansion is this. Nothing, you know that it is very simple. But then, how you will find the approximate value of root 10? Here, look at this root x, and then you have to consider x equal to something and h equal to something, and left hand side is actually square root of x plus h, that is what? 10. So if you take 9 and 1, okay, if you take x equal to 9, h equal to 1, Then left hand side is equal to root 10, and right hand side you have to substitute every value. Square root of x, that is 3, d dx of x to the power half, that is half x to the power minus half. Then you have to substitute x equal to 9, and here into h, that is 1. So in this way you will get this expression, and finally you will get this. So this is one application of the Taylor's theorem to find approximate value of any function. Okay, example is next example is evaluate evaluate 0 to infinity, 0 to infinity, e to the power minus x square plus y square dx dy by changing to polar coordinate. This example I have already solved in your class. However, still I have chosen this one because here the question is by changing to polar coordinates. By changing to polar coordinates, that's why I have taken this example, because you know that 0 to infinity, this example can be written, this example can be written 0 to infinity minus x square dx, 0 to infinity e to the power minus y square dy, because x and y can be separated, separate limit, and then you can easily evaluate this question. But here the question is find solve this example using uh, solve this example using by changing the polar coordinates, changing to polar coordinates. Hence, so that this equal to 0 to infinity to the power minus x square dx equal to root pi by 2. Here x equal to r cos theta, changing to polar coordinates. So x equal to r cos theta, y equal to r sin theta, and dx dy equal to j dr d theta. And already you are familiar that for this transformation j equal to r, so r dr d theta. And here look at this. If you change into polar coordinates and then change the limit, then it will be like this, and this equal to pi by 4. And next question is, next part is, so that this equal to root pi by 2. And it is, look at this, it is definite integral. So 0 to infinity e to the power minus x square and 0 to infinity e to the power minus y square dy, both are same. So it can be written as 0 to infinity e to the power minus x square dx whole square. So and this is equal to pi by 4. So 0 to infinity e to the power minus x square dx equal to what? Root pi by 2. Another problem. And also it is chosen because here a transformation, by changing the transformation here, change transformation is x equal to u minus uv, y equal to uv. That is, you have to solve what were the problem, probably, anyway, this is the problem, you must remember that this is the problem. And this problem is to be solved by the transformation x equal to u minus uv, y equal to uv, and this transformation is given that change this transformation, evaluate the integral. Question is this, change this using this transformation, evaluate the integral. So here r is the region, and r is the region, there is one mistake I think. Anyway, so if you consider this transformation, then your Jacob dx dy equal to what? Dx dy equal to dx dy equal to mod j du dv. So here j equal to what? J equal to, you know that already, dx du dx dv dy du dy dv, and that equal to, here if you evaluate, that is q. Now the limit also was given, but here unfortunately the problem is not different. So anyway, accordingly, limits this r, region r is not given. Anyway, what you have to do for the region r, the limits can be set for the variables x and y, but after this transformation your new variables are u and v. So u and v, you have to set up limit, and that limit is 0 to 1, 0 to 1, 0 to 0. And then it is not so difficult, you have to evaluate this integral. So my intention was that, uh, if question in the question, these two example, in the earlier example, change in polar coordinates, then evaluate. Here using the transformation, x equal to this, y equal to uv, change, evaluate the integral. So you have to change the variables, then you have to evaluate. Okay, next one is, so it is also being your practice. Find the asymptotes of the curve. Asymptotes of the curve. Y cube, find the asymptotes of the curve y cube minus x square y plus 2y square plus 4y plus x equal to 0. Find the asymptotes of the curve. Check whether you have in mind what is the procedure. Otherwise, I will discuss. So, what you have to do? What is the method? High-end method. Here it is. Look at this. It is a cubic equation. This first term is y cube, second term is x square y. So what you have to do, you have to replace y by m and x by 1, that I told you working method in your class. So the first phi 3m equal to m cube minus m. Phi 2 equal to what? 2m square. Phi 1 4m. In this way you will get 4m plus 1. In this way, you will get phi 3m equal to m q minus, that is m into m minus 1, m plus 1. So phi 3m equal to 0 gives m equal to 0, m equal to 1, m equal to minus 1. So fortunately, here all the three roots are different. So you will get three different asymptotes, and corresponding C can be obtained by using this formula. C equal to minus phi 2m by phi 3 dash m. This is the formula, you know that when roots are different, the corresponding C can be obtained using this. So for m equal to 0, C will be 2 0 square, 3 0 square minus 1, so 0. So asymptote is y equal to 0. Y equal to mx plus c, m0 c0, so y equal to 0. And for m equal to 1, c equal to 2m square that is 2, 3 minus 2 that is 1, 2 by 2 minus 1. So this one. In this way you will get other asymptote also. So this is the method you have to remember. And also I told you that what is written here I have already earlier also I have discussed. Still I to remind you I have again written it. Asymptotes parallel to the y-axis are obtained by equating to 0 the coefficient of the highest degree term in y, and if the coefficient of the highest degree term in y is constant, then obviously there is no asymptote parallel to the y-axis. So the asymptotes that we are getting using phi n method, we can determine asymptotes whether it is parallel to y-axis, parallel to x-axis, uh, neither parallel to x-axis, not parallel to y-axis, etc. But in case if there are any asymptotes which is either parallel to x-axis or y-axis, then that can be obtained, that is written in the note. Asymptotes parallel to the y-axis. Parallel to the y-axis obtained are obtained by equating to 0 the coefficient of the highest degree term in y, and if the coefficient of the highest degree term in y is constant, then obviously there is no asymptote parallel to y-axis. Similarly, we can conclude that asymptotes parallel to x-axis can be obtained easily by equating to 0 the coefficient of the highest degree term x. So, for this example, look at this. One asymptote is y equal to 0. Y equal to 0 means what? X axis. So this is asymptote is parallel to x axis. How this asymptote can be obtained even if we do not use this phi n method? Highest coefficient of the x. Highest coefficient of x is what? Sorry, highest power of x is what? X square. Its coefficient is what? Y. So if you set y equal to 0, it is getting the asymptote that is obtained, also obtained from phi n method, that is written here. This is very important. This is important because I solved one example. You could remember that in sometimes it is found that only asymptote, all the asymptotes are either parallel to x-axis or y-axis. In that case, you don't have to use any method. Just check the highest power of x, take the equal coefficient equal to 0, you will get the asymptotes. Highest power of y, take the coefficient of the highest power of y equal to 0 with the asymptote. So only 2-3 line you will not getting all the asymptotes. That's why I am repeating it. I am audible.
Yes, sir.
Okay. So how many? Probably I was disconnected.
No, sir.
No,
No, sir.
not this. Okay. It seems to me that I was disconnected. Anyway, I will solve one two more. Then, oh sorry. This is not your life. Instead of taking break, I think I will continue. Then I will finish it. Some more examples are solved. One example, look at this. First, read yourself, try to understand, then I will explain. Using mean value theorem, find the point on the curve y equal to log x at which the tangent to the curve is parallel to the chord joining the points 1, 0 and b1. Try to understand the problem. Then I will explain. So you can get an idea that in which mean value theorem tangent is parallel to the chord joining any 2 points. You know that it is Lagrange's mean value theorem. And the geometrical interpretation of Rolle's theorem, you know that there exists at least 1 point at which tangent is parallel to the x-axis. And in Lagrange's mean value theorem interpretation is geometrical interpretation is tangent at any point is parallel to a chord joining 2 points. So here the 2 points are given. Here the 2 points are given at 1, 0 E1. So y equal to log x is the function. So 1, 0 E1, that is x1 y0, and here x e E1. And you know that the statement of the Lagrange's mean value theorem, if a function is continuous in a closed interval a b, derivable in the open interval a b. So here the interval is actually E1 E x coordinate, here x coordinate. So x coordinate fx function constant continuous in the closed interval 1b and differentiable in the open interval 1e. Y equal to log x function, known function, you know that it is continuous and differentiable 1 by 1e. And Lagrange's mean value theorem, you know that fb minus fa by b minus a equal to f dash c. C lies between a and b. So here fe minus f1 by e minus 1 equal to f dash c, and fx equal to fx equal to log x, f dash x equal to 1 by x. If you substitute here f dash c, then you are getting c equal to e minus 1. So the point is what? Point is E minus 1. It lies between 1 and E. 1 and E. 1 minus E, sorry, E minus 1. E minus 1 maybe, yeah. So this is an example of the mean value theorem that based on the geometrical interpretation of the Leibniz mean value theorem. And the next example is, if rho and rho dash are the radii of curvature, you know that what is the radius of curvature. Here two radius of curvature, that's why its plural is radii of curvature. At the extremities of the two conjugate diameters of the ellipse, x square by a square plus y square by b square equal to 1, prove that the relation is this one. So you have to actually find the radius of curvature at 2 points, and your sorry sorry it is ellipse. X square by a square plus y square by b square equal to 1 is the ellipse, and any point on this, say P, here if you take any parametric point, you know that parametric point is a cos theta, b sin theta. And here look at this, in the given question, rho and rho dash are the radii of curvature at the extremities of two conjugate diameters. You know the definition, what is the conjugate diameter. So if you take this point a cos theta, b sin theta, what will be the end point of this if these two are conjugate diameters? That is a cos theta plus pi by 2 and here b sin theta plus pi by 2. So these are 2 points. One is a cos theta b sin theta and another is a cos theta plus pi by 2 b sin theta by 2. Here you have to find rho and here you have to find rho dash. You know the formula for the radius of curvature for the parametric form, and if you forget the parametric form, then no, don't worry, x dash y dash, from here you can write dy dx. In this way also you can obtain, but I would prefer the parametric form because uh, it is not so difficult, simple formula. So x prime x dash x dash square y dash square x dash y double dash minus y dash x double dash, and if you substitute all the derivative you will get like this. Similarly, for rho dash, your point is what? This one, this one, parametric one, x equal to a cos theta plus pi by 2 and y equal to b sin theta plus pi by 2. Look at this. This one, and what you have to establish, you have to establish rho to the power 2 by 3. Just a minute, first erase it. Rho to the power 2 by 3 plus rho dash to the power 2 by 3 into ab to the power 2 by 3 equal to a square plus b square. So first add here rho to the power 2 by 3, and next rho dash to the power 2 by 3, add this. New denominator is same for both. So if you take the denominator common, the denominator, then a square sin square theta, a square cos square theta. So a square, b square cos square theta, b square sin square theta. So b square. Hence the proof. This is one very good example. Okay, next one more example. Z equal to f x plus a y and plus phi x minus a y. So that this one simple example, still as it is in functional form, that's why I have it is chosen. Z equal to fx plus a y plus phi x minus a y, x f x plus a y plus phi x minus a y. So that z y y equal to a square z x x. Very simple. Zx equal to what? Zx equal to f dash x plus ay del x of x plus ay. Phi dash x minus ay del x of x minus ay. So del x of x plus ay means 1. Del x of x minus ay means 1. So it is f dash x plus ay phi dash x minus ay. Similarly, if you differentiate again, uh, then also you will get zx. Similarly, you will get zyy, and find the relation. You will get this relation. Not so difficult. Okay, next example is if z equal to x to the power 4 y square sin inverse x by y plus log x minus log y, so that is equal to this. You can just differentiate, then multi. If you can do del z by del x, then multiply this by x, then del z by del y, multiply this by y, then take their sum. You can get this one, but it will take some more time. But if you use the if you use Euler's theorem on homogeneous function, it will be easier. Why? Look at this. This part is taken as u, this log x minus log y, that is taken as g. So if you consider u equal to this, it is a homogeneous function of degree 6 because x by y, that is 0, and here x to the power 4 y square, so it is a homogeneous function of degree 6. So by Euler's theorem, this one 6u. And if you consider v equal to log of x plus y, x by y, then it is a homogeneous function of degree 0 because there is only constant 1. So degree 0. So by Euler's theorem, this one. Now add these two, x del x u plus v, y del y u plus v, u plus v equal to z. So x del x of z, y del y of z, and equal to 6u plus 0, that is 6u, and you know that u equal to what? U equal to this one. So and you have to establish this one. So hence to. So you can do it in normal way by taking partial derivative with respect to x, then multiplying this by x, again taking partial derivative with respect to y, and then multiplying this by y. But I would suggest you to do in this way. Okay, so that's all. Some examples are solved. Hope it will be useful for you. If I if you attend the class, I will solve some more example in the next class, as it is found only few 4 5 students are joined. That is only 4. Okay, that's all.
Sir, please share this material.
Yes, yes, of sure. I will upload this file. Yesterday I have collected this example. Today I will upload this file. Okay.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.